Okay, good morning, everyone. Okay, today we are going to talk about data compression. For those in 355, we also will look at data compression in that class, although our goals, our motivations, our objectives in discussing data compression is different in the two cases, right? In the case of networking, we want to use data compression more in terms of the goal of reducing footprint. In this class, we're interested in the algorithms themselves and the time complexity and the performance of the algorithms. So we're going to look more specifically at 4 different data compression algorithms. All 4 algorithms are going to be what's called lossless algorithms. We'll explain what that is momentarily. But first, to try to understand why data compression is an important problem. So if we are able to compress our data, it takes up less space on our drive. It also takes less time to search for it, although that's not entirely true, because if we can't interpret the data during the search because it's compressed, then it doesn't necessarily help us. So that depends on the form. Certainly backups will be faster, right? Because again, we're backing up a compressed version. And if it's being stored in a smaller way, so if we need to transfer it from one place to another, including, let's say, over the internet, but it could be a local, moving it to USB drive or something like that. So it will be faster as well. So we have 2 primary means of data compression. One is called lossy and one is called lossless, right? Lossless data compression means that we compress the data and eventually we decompress it. So for example, we unzip the files, right? And we get back exactly what we started, okay? So we call that lossless. And most of the compression that you use deliberately, when I say deliberately, I mean you are trying to compress the data, so those are lossless methods. However, there are many methods that we use without necessarily even realizing that we are compressing data, and they are lossy. Lossy means that the input to the compression algorithm and then doing something with it and then decompressing it, we don't get back what we started. I have an interesting story about that, but first, another detail here. A few details. Okay, so first of all, it's irreversible. Okay, so again, what you put in is not what eventually get out. Another is it's intermittent sampling. What that means is, let's say you have a video camera, right? The video camera is, taking images all the time. Well, we don't actually use all those images, right? We use frames from a sample, let's say every 30th of a second. Okay, so someone, I don't know if it's a ophthalmologist or neuroscientist, someone figured out that the brain, the eyes can't process samples more than that. So there's no point in having more samples. All right. So we don't send everything. Or if you're listening to audio, right? So we send the voice that's being heard on the microphone in the room. We don't send that continuous, right? We also have that with the pictures, right? So we don't send every single bit exactly, right? There are algorithms for that. We're not going to study them in this class today, but things like JPEG, MPEG, MP3, and so on. So here's my little story before we start to get into some of the algorithms. I did something interesting with my class during the year, and we took a text and we converted the text into an image. Okay, so we took a text and we made it look like an image. It was random pixels of different colors, so it didn't really look like anything in particular, but it was a very cool look. Actually, we did it on Pi Day, so we made it into a circle. So you had this circle with all these random colored pixels. It was pretty cool. But to really complete the exercise, at the end of the class, I said to them, okay, let's do the inversion, right? Let's see if we can get back the text from the image. And what we found is it wasn't working. And what do you do? So you debug and you debug and you debug. And then I realized, you know what the problem was? We made it into a JPEG, and a JPEG is lossy. So if you undo it, it's not going to work. All right, so what did we do? We then did it again. We just had to change the format of the file into a BMP, a bitmap file, and that is not lossy. Okay, that is not lossy. And so then when we took the algorithm that we coded to decompress it, it came back exactly to the text perfectly. So it was actually pretty cool. So once you can do with random colors, you can also make it grayscale. You can do a lot of different things, and it almost becomes like a kind of cryptography, right? You take an image and you send it, and to an onlooker, it looks like an image, but it actually can have all kinds of text encoded inside it. It was pretty cool. All right, so before we, here's a question for you. If we have lossy techniques and we have lossless techniques, why would anyone choose lossy if we have lossless techniques? Let me give you an analogy for a second, right? So let's say I have two kinds of wallets I can sell you. I have wallets with holes in them where some of the money will fall out, and I have wallets that don't have holes where the money doesn't fall out. Which kind of wallet would you buy? Probably say, well, buy the wallet that doesn't have a hole in it because you don't want to lose your money. Okay, so why would we take a lossy data compression technique? Someone was about to say something. I cut them off. I apologize.
I think it's like the UDP one when the lossy part doesn't really important. The one package, like if we send a text image to my friend, the quality of the picture doesn't really matter as long as the
okay, right. So it could be that it's not as critical. Very often you won't know the difference. Okay, so whether you save something as a JPEG or a BMP, you know where you're going to see the difference? When you go to File Explorer or whatever the equivalent is on a Mac, and you look at the size, you'll notice a difference. You'll notice the BMP is big and the JPEG is small, and that's what you'll notice. In terms of actually looking at the image, unless you're like a graphic designer and you have a really fine eye for this stuff, or you do an experiment like the one I just described, where you're actually encoding text inside the image, you know, in a hidden way, you won't notice the difference. All right. So these are the techniques we're going to talk about. So the bottom line is, A, you don't necessarily notice the difference, and B, you can't afford the lossless, okay? Because the lossless just doesn't give you the same rate as the lossy, particularly things like sampling, right? I can't send every single possible frame of the video. It's too expensive, so I sample every 30th of a second. Right, so these are the techniques we're going to look at today. First one is very simple. The second one you may have actually seen before in your data structures class, or perhaps somewhere else. And then we have the two others that, unless you maybe you did it somewhere, but so. All right, so the first one's called run length encoding. It's a pretty simple idea. I've given this as a problem to my intro students. Doesn't mean they all did it correctly, but it's a very simple idea. And it says as follows. Let's say you have a text. Let's say you have a text, and it happens to have, you know, sort of a relatively small alphabet, which means, you know, the same characters repeat themselves a lot. All right, they repeat themselves a lot. So instead of, you know, writing A 10 times and B 6 times, well, let's take the example that you see here, right? So instead of writing A 8 times and B 5 times, and then you write A, what is it, a 6? You write A 6 times, right? You say, well, you know what? Why don't I just say 8 A's and 5 B's and 6 A's? That's shorter than actually writing them all out, right? Here are some other examples of that, right? So back in the day when we were, you know, we sat in a lecture hall and you would write on the board. So in some of the rooms, they had blackboards. So you have a blackboard that's mostly black or green, right? Blackboards are often green. And then you have in other classrooms, you have a whiteboard, and the whiteboards are mostly not white, but like gray. And then, you know, here and there you have some magic marker that's black or purple or green or something like that. my dry erase marker. So it's mostly, if you encode that, it's mostly zeros with a little bit of ones, or it's mostly ones with a little bit of zeros. So this run length encoding would be a very good approach. It says just keep track of, each different type of character. In fact, you can go one step further and you can say, let's say it's a white background. So in a white background, I don't know if you know the HTML behind it or the coloring scheme, but in RGB, that's going to be all ones. FF, the hex, which means all ones. Okay, so that's a base 250. Each number is 256. So each one is going to represent 8 bits, 8 1 bits. Okay, so that's 24 bits. So instead of just, most of it's going to be ones. Just keep track of the zeros. Okay, just keep track. You write down how many ones you have, and then you have a zero. How many ones you have a zero. So that's a variation of that. A variation of that, where you just keep track of one thing. You don't even have to keep track of the other. So we call that run length encoding. So again, this is an analysis of algorithms. So can someone tell me, as a function of the length of the text? So let's say we have n characters. What's the time complexity of this? How long does it take to go from, let's say, this text here to this version on the right side?
O of n.
That's an O of n, right? It's an O of n because I just need to make one pass through, right? Each time I start a new letter, I keep track of how many of that letter I have. When I get the next letter, I renew the count and I output what I had so far. Okay, so here is some actual code. Makes it more obvious that it's O of n in case you didn't trust Ilma, very trustworthy student, but in case you didn't trust her. So there you have a loop. Okay, so we check, right? If the character is the same as before, we say the run continues, right? Otherwise, the run ends. We print out what we have so far, and we set the new run as having a size of 1 for the new character, all right? So that's a very simple algorithm. Okay, and it's O of n, all right? I don't know if we talked about this in this class. I gave that if you've looked at my old exams. So on one or more of my old exams, I had something called a streak sort, where basically you're looking for streaks. A streak is a run of numbers that are all in increasing order already, and then you have another streak. So it's a sort of a cool question. I encourage you to go look at it on the old exam. But it's my understanding is it's somewhat similar to TIMSORT. Okay, because what are you really doing? You're doing merges, but not merge like in the regular merge sort. You're doing merges of different streaks. Okay, so you start with the smaller ones, you merge them into bigger ones. Okay, so that's a run length encoding. As I said before, there can be some variations on that, particularly where you have a lot of one thing and an occasional of the other, right? So we could say, I have 17 zeros followed by 0 zeros. Why 0? Because I have 2 ones in a row. Then I have 0 zeros because I have 2 ones in a row. Then I have 5 zeros, 1, 2, 3, 4, 5, okay? And then I have 0 zeros, and then I have 6 zeros. By the way, why am I using 2 digits? Okay, let me just be clear. This 0, 0 doesn't mean 0 zeros. It does mean that, but that's not what the 0, 0 stands for. It's saying 0. And this is saying 5. This is saying 0, and this is 0, right? Whatever we're talking about is how many zeros are between a pair of ones. So why am I using 2 digits here? I don't have to. I could do this with 1 digit. I'm using 2 digits because if I expect to get a lot of zeros in a row, then I need more digits to represent that. So if I don't expect to get many zeros in a row, then I'll use only 1 digit. But this way I can go as much as 99. Now what happens if I get 127 zeros in a row? Then I'll do 99, and then I'll consider it to be like another block, all right? So that was sort of easy. We move on to our next one, which is a little bit more difficult. It uses a greedy strategy. So some teachers of algorithms, well, there's no guarantee what anyone's going to do in their course, but many teachers will teach this not as part of data compression, which they may or may not talk about, but they'll do it as part of greedy algorithms, right? So the first thing to appreciate is that, let's say back in Intro to Computer Science, when you learn a little bit about characters and so on, you understand that there's something called ASCII, an ASCII character set. An ASCII character set has 7 bits, and then there's one more bit, kind of parity check, right? So we have either 7 or 8-bit alphabet, and there are bigger alphabets, right? So today we have all different kinds of character sets, different languages, mathematical symbols, emoji, or emoticons, or whatever those things are called, right? You got all different kinds of interesting things out there that are part of the official Unicode character set. So we might have even more bits, but for our purposes, let's assume that every character is an 8-bit representation. Now that means that whether it's a let's say a sad face emoji, or whether it's the letter E, or the letter Q, or the bell. Did you know that there's an ASCII character number 7 for the bell? They're all going to have the same, not the same 8 bits, but they're all going to use 8 bits. Obviously different numbering system depending on which one they are, but they all use 8 bits. So what's the problem with that? The problem with that is, wouldn't it make sense if the things we use often, like the letter E, or a carriage return, or a space, right? Those would use less bits because we have them all the time. And the things that are infrequent, some weird, character that no one ever knew that even existed, that'll have a larger, maybe more than the 8 bits. So it would be nice if our E only took 2 bits, let's say. And if, the letter Q, which doesn't happen so often, is 12 bits, okay, it'll be 12 bits. So that's the idea. That's the motivation behind Huffman coding. So who was this Huffman? Huffman was a grad student in MIT in the early 50s. My understanding of the story was that he did this in lieu of an exam. So they had a choice. They could either take an exam or do a series project. So 70 years ago, he designed an algorithm called Huffman coding, and it was so good that teachers like me still teach it in our algorithms classes today, right? So again, it assumes that it's a variable length representation, right? Not assumes, it makes it into a variable length representation, and it's based on frequency. So the first thing it's going to have to do is figure out the frequency of the various letters in the text. Okay, and then what you get is an octal prefix code, right? It figures out what each letter should be represented by relative to its frequency. And it is a greedy strategy, as we'll see soon. So here is the pseudocode, if you like, or the basic strategy. So it's not really pseudocode, it's an outline, okay? So first thing we do is we need to determine the frequency of each character in the text. Can someone tell me something we've learned in this course that essentially was doing that?
Radix sort.
Very close. Radix sorts 1 digit at a time and uses, what does radix sort use behind the scenes?
Counting sort.
Counting sort. Okay, in fact, the counting sort that was on Geeks for Geeks, it was character based. So I'm not even sure if all those counting sorts that people did worked. I don't know if people tested them or not, but the way it was coded was for a character set. So you had to find a different version of counting sort, or you could change it. You could change the version there. It's not too hard, but you'll notice it was looking at 256. So that's the character set, right? That's the ASCII character set. All right. So we use something like a counting sort, right? We keep track of how many, every time we have an A, we increment the bucket for the A's. Every time we get a B, we increment the bucket for the B's. Then we sort the frequencies in non-decreasing order. Non-decreasing is a fancy way of saying increasing. The reason we say non-decreasing is because we may have 2 frequencies that are the same. That happens a lot, actually, especially if the text isn't that big. Right? You could have, the same number of R's and S's. Okay, so it's a greedy strategy. Why is it greedy? Because we're going to take them in non-decreasing order, meaning, smallest first. Okay, so it's sort of like fractional knapsack and Kruskal's minimal spanning tree algorithm that we talked about yesterday, right? Both of those involve sorting, and then we took them in smallest to largest order. Actually, in fractional knapsack, we did the opposite, right? We took the largest value per weight. So it was a decreasing order. In Crusko, we used an increasing order, but in both cases, we used a greedy strategy. Take the largest first or the smallest first, depending on the algorithm. All right, then we build the Huffman tree. And I'll talk about that in a moment, but before we do that, what kind of sort should I use? What kind of sort should I use? So that's the question we always need to be asking ourselves. Anytime we see the word sort, what kind of sort should I be using? And at this time, you should be experts in answering that question. So you should say to me, it depends, and then I'm going to say it depends on what, and you should be able to answer that. So it depends on whether we are dealing with, let's say, finite precision, floating point numbers, right? If it could have an arbitrary number of decimal places or digits, then you can't really use a counting sort or radix sort. But if I have a fixed number, so let's say all the frequencies are going to be integers between 0 and 100, right? Or maybe, between 0 and 10,000, but it's a nice, it's a nice fixed interval, and there are no decimal places. Or I do a probability, but I'm going to round the probability to 3 decimal places, right? So I can use a radix sort for that, and I can get a linear time. All right, so we're going to come back to that question a little bit later. Now we get to the guts of it. Okay, so we build the binary Huffman tree. We take the next 2 lowest frequencies, right? So the next 2 off of the list. We make them the left and right children. Generally speaking, we want to follow the convention that the smaller will go on the left, the larger of the 2 go on the right. So it's a little bit like a heap, but not exactly like a heap. And then the parent node will be the sum of the frequencies. Okay, so unlike a heap where the parent node is, its own key, its own data. Okay, in this case, the parent always represents the sum of the 2 children, which will obviously guarantee that it has a proper parent-child relationship for a heap, right? And you keep doing this until you've gotten all the nodes and all the frequencies, and the total frequency will be 100%. All right. Now, how do we encode the data? You trace a path from the root to the character you're interested in, which will be in the leaf. And every time you go to the left, you put a 0, and every time you put a right to the 1. So what does that mean? It means that the nodes that are closer to the top will have short encodings, and the ones that are further away will have large encodings. So we're going to run through an example, okay? Always better to have an example. So this is a very simplified example. We have all of 6 characters, and the total number of characters in this text is 100. So it's, 6 different letters, but the total number of occurrences, the frequency is 100. And we did a calculation, right? We ran through the text ones, and we determined that there are 45 A's, 13 B's, 12 C's, 16 D's, 9 E's, and 5 F's. Okay, probably not like a regular text, right? First of all, we would obviously have bigger alphabet, and number 2, you would expect to see more E's and less F's, for example. Okay, maybe it's like grades in our class. We hope that there are a lot of A's and just a few F's, right? Probably this is different than our distribution will be, but okay. 0 F's. Yeah, well, some people ask for F's. They actually ask for F's. They say, can I have an F? I get that question from people, believe it or not. Okay. All right. And there are other grades, right? People disappear. They just don't show up. So they get a woo grades. Okay. All right. So what are we going to do? Well, we're going to take the 2 smallest. The 2 smaller are the 5 and the 9, and we combine them for a frequency of 14. The next 2 smallest are 12 and 13. Combine them for a frequency of 25. Then we take the 14, which was a combined frequency over here, with the 16, which is the actual frequency of D, and we combine those, we get a frequency of 30. And we take the 25 from here to the 30 from there, we combine those for 55. We take the 45 and the 55, and we combine them for 100, and we have a beautiful picture here. Now, let me point out something here, right? This is a fixed length code word, and this is a variable length code word, all right? Take a look at this picture over here. Okay, how many bits will it take to represent F in this picture on the left? Want to write it in the chat?
3.
3. Okay, by the way, did I tell you about my chat analyzer program? I mentioned it in 355. So I wrote a program which analyzes the chat logs, and it goes through the whole semester of chat logs, and it organizes it by student, and it tells me exactly how many times each student participated on the chat. It tells me what they said. So were they asking for the top hat code an hour into class to let the whole class know that they were an hour late? Or are they contributing in a meaningful way? Are they answering the question? So I learn a lot about what students are doing and what they're not doing. And then the other thing that's very interesting is we tend to get, about 95% on the top hat attendance, even though the number of people who actually attend the class at all, I'm not even talking about if they're paying attention, but actually are on the Zoom at all, is more like 50%. So that's an interesting statistic, the details of which are very aware to me. Okay. All right. Okay, so Ilma is correct. Okay, Ilma says that the fixed length encoding of the letter F will be 3. And just for comparison's sake, what is the fixed length encoding of A?
Also 3.
Also 3. Now let's look at the variable length encoding on the right-hand side. And what is the encoding for F?
4.
4 characters, right? 1100. Everyone see that? 1100. And what is the encoding for A?
Just 1.
Just 1. Correct. Okay. So let's think about, let's analyze. We're not analyzing the time complexity at the moment. We're analyzing the performance, if you like. Right. So it's a different kind of analysis. It's also analysis not of time complexity, of space complexity, but of accuracy, or it's not even accuracy because they're both completely accurate. Just I guess compression, performance. Okay, so in this example here, even though these are ASCII characters, but we don't really need an ASCII encoding. We only need 3 bits to represent them. So if I have 100 characters, because that's what the example said, right? Get a total of 100 characters, right? Each one takes 3 bits. So the total is 300 bits, 300 bits. Okay, let's do the variable. Okay, so Ilma told us 1 bit for A and 3 bits for, 4 bits for F. Okay, and there are 5 of them, so we get 20. So if I do that for the others, I get these numbers of bits, I add them up, and it's 224. In other words, to use the variable length encoding of these 6 characters in that text, I need 224 bits. Okay, so what is my compression rate? The compression rate is equal to the uncompressed text over the compressed text, which is 300 over 224, which is 1.34. Okay, so that's, I don't know if that's good or bad. What you have to do is you have to look at, compare it to other algorithms. You look at other texts, right? Some texts don't lend themselves well to this variable length. Can someone tell me when this would be good? When would Huffman be good? Or when do you get the most bang for the buck, as they say?
When I'm sending a message to someone else.
Well, that's when we care about this, but what kind of scenarios would this Huffman work better, and when does it not work so
when
well?
we have a lot of repeating characters, right?
Yeah. I mean, the run length encoding is where you have the repeating in a row. So here's where I think you're going to get the bang for the buck. You get it when the data is not so uniformly distributed. Okay, when you tend to have, certain ones that are very frequent and other things that are less frequent, right? That's when you get the good bang for the buck. So if you have random data, okay, 0s and 1s, random, it's good. If it's not so random, or let's say it's ASCII and some of the characters are frequent, appearance, right? So that's when it tends to be good, because then that discrepancy between the smaller, the more frequent and the less frequent, more frequent get the smaller ones, the less frequent get the bigger ones. So you get more more example. Okay, and then we have just to show you the encoding, right? So the way the encoding works is we use that tree that you saw on the right-hand side, give the encoding of those 3 letters, and you get this. And you'll notice, by the way, that no one thing is a prefix of another. So that may not be obvious to you, but let me point it out, right? If A is 0, nothing else begins with 0. Everyone see that? Okay, if C is 100, nothing else can begin with 100. If B is 101, nothing else can begin with 101. That's important because if I'm decoding it, like I do over here, I need to understand, is that 100, is that a character, or is it 1001, which is something else? So I can't have a situation where something is the prefix to something else, right? That will create confusion. So now we get to the sort of algorithms part of this, which is, okay, so we had some code before. How do we implement it? So first of all, we have to keep track of the frequencies. Okay, so we could use like a hash table, or in Python we call it a dictionary, right? Keep track of that. Or we can use an array like the counting sort. Actually, the counting sort example from Geeks for Geeks is basically tabulating frequencies. Which one do you think is preferable? So which of those 2 options you say is better?
Hash table.
Well, it depends. Okay, if you have a series of letters from one alphabet, right, and you expect to get some of each of those, right? So let's say you're doing the ASCII character set. So an array is good because it's all sort of contiguous, right? It's all very organized. If the things could be all over the place, right? Let's say there are words. Okay, usually we do this with characters, or the characters are not just the ASCII, but we've got Unicode characters. So we've got some Hebrew, we've got some Arabic, we've got some Chinese, we've got some Spanish characters that are not in English. We've got French, we've got all different kinds of things going on in there. So it's not 256 characters anymore. So to have an array for every single possible character is not really good. So in that situation, a dictionary might be good because you're going to have characters that are all over the place that need to be in this data structure. Okay, so those are 2 options on the frequencies. Then we get to the sort. We already discussed this, right? By default, we always have our fallback, let's say, the heap sort, the merge sort, both n log n. Quick sort can be done in worst case n squared, but on average is n log n. We have the Tim sort, which is n log n. All right, but we try whenever possible to see if we can use a linear time sort like the radix sort. And then comes the interesting part. Okay, so you sort of should have known about those 2 things before, but here comes the interesting part, right? We need to choose the next 2 smallest. So how do we do that? So let's break up the question. How do we find the smallest thing in an array?
Min heap.
No, just if you have an array, how do you find the smallest thing? So let's say we have an array of all the sizes, like using one of these, or a list, or a table for that matter. How do you find the smallest?
Just compare all the elements.
You loop through all the elements. Okay, so and how long does that take?
All of n.
All of it. Good. All right, now we need to do that each time. So we're going to do the n times, so now it becomes n squared. Good. Now, Elma, you already mentioned something before. Now we're ready for that. We could store it in a binary heap. So in a binary heap, the min is on the top, and we always have to restore the heap. So we're going to do that n times, so we get n log n. All right. Now comes the interesting part. Okay, so those 2 ideas I would actually expect you to be able to come up with on your own at this point, even if we didn't have this lecture. But the next one is sort of a clever trick. It's not my trick, but it's a clever trick. It says, let's use 2 queues. Okay, we're gonna have 1 queue. So let me just show you back here. Okay, so we're gonna have 1 queue for the original frequencies. When I say the original frequencies, I mean this list here. And then we have another queue for the combined frequencies. Now, what does that do for us? Remember, once we sort the frequencies, they are in sorted order. That is never going to change. So we don't have to worry. Where is the min going to be in a sorted list? Where is the min in a sorted list?
The start at the end.
It's at the start or at the end, depending on the direction. So in our case, it's going to be sorted in increasing order. So the min is going to be the first position. As we remove things, it'll always be in the first position. So it's easy, right? We just do O of 1 right at the beginning. Okay, but the problem is that as we combine frequencies, we get new numbers, combined numbers that weren't there before. Well, instead of putting them back in the original list, where they're either going to be out of order or we have to restore a heap or something, we put them in a second list. And the combined frequencies are only going to grow. So that second list will also be in sorted order. So where are the two smallest? They're always in either the first, the first two positions of one list or the first two positions of the other, or some combination. But you never have to go beyond the first two positions to find the next two smallest. So the cost of that is O of 1, meaning at most 4 operations times n, because again, in all these cases, we need to do this n times. So it comes out to be O of n. So that's a neat trick that you can use to improve Huffman, right? So when you think about that for a second, that means we can get Huffman down to an order n algorithm, because we can do the frequencies in O of n. We can sort them. In most cases, we can sort them in linear time. And then we can do the, getting the next two smallest also in linear time. So we can make the whole Huffman in linear time. So that's pretty cool. And this is an algorithm for it using essentially the heap approach. Okay, so the middle of those 3 approaches. Right. We move on to the third of our 4 compression algorithms. Okay, this is called Lempel, Zeev, Welch. Okay, Lempel and Zeev were 2 scientists who originally came up with this methodology. Then along came someone by the name of Welch, who made various contributions and improvements to this algorithm. So he got his name and his initial into the algorithm as well. Okay, so this is what we call a dictionary-based approach, and until you actually see it in action, it's very hard to understand. So an example, as usual, will be important. Okay, so again, it was 2 fellows by the name of Lempel and Zeev, 1970s. Harry Welch came along and improved it in the 80s, so he got his name in it. It's a dictionary-based encoding. So what's the basic idea? The basic idea is to say, instead of a series of characters, we're going to use an ID. We're going to let a number represent a series of characters. Anyone know this joke? It's a joke about jokes. So you have a bunch of prisoners sitting around in the cafeteria of the prison, and they're telling jokes to each other because they don't have a lot to occupy themselves with, so they tell all the jokes that they know. So, but instead of telling the joke, the way we normally tell a joke, they just say, they call out a number. So one guy says 45, and all the guys start to laugh hysterically. And then another one says, oh, 62, and they're rolling on the floor. Another guy says 34. So there's a new guy in the prison, and he says, so he's going to do that. So he says 74, and no one laughs. So he says, I don't understand. When you guys tell the number, everyone's laughing so hysterically. LOL, right? LOL, we're all laughing out loud. And when I call out a number, don't you say, that's an old joke. 72 is an old joke. All right, so that's essentially what we're doing over here, right? We are assigning an ID, not to jokes, but to text, all right? So the question is, how do you make that assignment in a good way? So we're going to show you how it works. But I will say this, LZW is widely used, all right? It's widely used behind the scenes, all right? So if you're using any kind of compression, there's a high likelihood that somewhere in there, it's either LZW or some variation on the LZW theme, and I'll explain to you how you might have variations. So some of the things you can do to sort of mix it up, make it a little bit more interesting, all right? So just to drill down a little bit. Okay, so the first thing we need to do is we need to choose a size for these IDs. Okay, because here's the problem. The problem is if you make the IDs too big, then you're replacing a few characters with a big ID that's not saving any space. So it's a balancing act, right? The more IDs you have, the more things you can substitute for. But if you make the IDs too big, then it may not be worthwhile. So again, you have a balancing act. So what I'm writing here is there are two choices that are sort of popular, right? One choice is to use an 8-bit ID, okay, which means that each of these IDs has 8 bits, so it can give you up to 256 different values. Or we use a 12-bit ID, which means we get up to 4,096 values, right? Okay, so that's one thing. Then we encode the character set, right? So you take your alphabet, and those need to have IDs associated with them. So there you don't get good bang for the buck, right? Because I'm taking maybe a 12-bit ID to represent a letter in the alphabet, so that's not such a good deal. However, as we go on, right, now I'm going to have IDs representing bigger series of characters, and I get more bang for the buck. All right. So here is the pseudocode. The pseudocode says as follows. Right. First of all, I need to assign IDs to all my single character strings. Okay, single character strings is another way of saying my alphabet. Right. So what is my alphabet? My alphabet could be something simple like ABC. It could be the whole alphabet, ABC through Z. It could be AB3 through Z and the lowercase ones, if it's case insensitive. It could be the whole ASCII character set, 256, maybe something else, right? But I need to initialize that first because after we also represent individual characters. Then what I do is I start to read from the character set. And I say, if I take what I have so far, with that one more character, if that's already in my table, then I try again. I try to look at the next character and see if I can get an even longer string. If not, then I need to output the code for what I had so far, and I need to update the dictionary to have the old string with the new character, and that will become part of it. All right, so that's what I'm doing. So I'm gradually writing down these IDs that correspond to substrings of the string. So instead of sending the string, I'm going to send a sequence of IDs. So again, we're going to do an illustration here. So let's say I have the string abracadabra. Okay, magic word abracadabra. So what do I do? What do I do at the beginning? Well, remember the rule is I need to initialize my dictionary. So we're going to assume that the only letters that I have available are A through Z and space, right? The space character. So I need 27 characters for that, right? So I'm going to make 0 my space, and then 1 through 26 will be A to Z. Okay, so again, you have to adjust based on your alphabet, and you have to know if it's case sensitive or not. But we're going to assume everything is capital letters, all right? So we're going to work through this string, and we say as follows. Is A in the table? What do you say? Is A in the table?
Yes.
It is. Okay, so what I do, if it's in the table, I attempt the next letter together with it. So I look at AB. AB is not in the table, so I output the 1 for the A that I already have, and I add AB to the table. Now, what ID is AB going to get? It's going to get 27 because that's the next available ID. Then I say, okay, so I have a B. Why do I have a B? Because the A got taken care of already. So I have a B. B is in the table. So I look at BR. BR is not in the table, so I output 2 for the B. I add the BR to the table, and I continue with the R. So R is in the table. I try to add A. RA is not in the table, so I output the 18. R is the 18th letter of the alphabet, right? T is the 20th, that's how you remember it. And then I add RA equals the next number, 29 to the table. I'm back to A now. A is in the table. C is not in the table. So I output the 1 for the A, just like I did back here. And I add AC to the table. Okay, C is in the table. Move on over here. CA is not in the table. So I output 3 for the C, and then I add CA to the table. So I have A. AB is not in the table. You get the idea. Let's find one where, okay, look at this. Okay, so remember what happened over here? AB was not in the table, so I needed to add it. Okay, this time, right, it's abracadab, right? This time, AB is also in the table. So I'm going to try the next letter as well. So ABR is not in the table, so I output the 27. Where did the 27 came from? It came from over here. I output the 27, and I add ABR to the table, gets 34, because that's one more than the last one that I used. And the last letter needs to be considered, because we outputted the 27 for the AB, so I have this R here, so I get R equals 18. Okay, then I get the next letter A. That's actually the last letter in the sequence. I wrote 29. Oh, RA 29 is in the table. Okay, where was that? That was over here, right? RA became 29. So it's in the table. I output 29 for the RA, and I'm done. Okay, so I don't know if you can see this. If this is blocking, I'm going to move this out of the way. So here's the output. Okay, so I have a bunch of numbers, and they correspond to the characters. And notice the way I wrote it here, right? The ones that got combined, there's the numbers 27, 29 corresponded to these composite characters. All right, so that's the LZW. So we call it a dictionary-based approach, because that's what I'm doing. I'm building a dictionary. What is a dictionary? It's a mapping, right? It's a mapping. So I'm mapping little strings, series of characters to numbers. Now, when will this be good? So it's not really good for, short strings, okay? You get more bang for the buck here when you have a long string, because that's when the patterns start to repeat itself. And so you can get, 6 characters in a row that are represented by, let's say, a 2-digit number. So now you're starting to see cost savings. Okay, so you don't do this with a few characters. But yeah, big enough, it becomes worthwhile. So here's our code. Let's just walk through this code again. Okay, this is Python code. And it says, okay, so first of all, you have to decide on your dictionary size. So that's 8 bits. You could also use 12 bits, which is going to be 4,096 possibilities. And initially, our dictionary is just the character encoding. Okay, so what we do is we look at the characters in the uncompressed. Uncompressed is the text, the original text, and we build up a string of what we have so far, and we say if it's in the dictionary, then we use this character here. Okay, so the W will represent what we had before plus the new character. If it's not in the dictionary already, then we need to add the W to the dictionary, and our number, so dict size is the number. So that was the 26, the 27, the 28, the 29. So we need to add one to the dictionary, and we assign that number, actually the previous number, to that particular string. Okay, the string that wasn't in the dictionary, right? So WC was not in the dictionary. That's why we're in the else case. Okay, and there is an important point. So if you land up ever implementing this, you have to remember, don't forget about the last little piece. So chances are, didn't happen in this example here, but in most cases, chances are that last little piece will not have already been in the dictionary. So don't forget to output that last piece, an ID for the last piece, because otherwise you're going to be missing the end of the string. That's a very common bug that happens in the implementation, right? So people remember all this, and they forget that last little if thing at the end. Right, so what is the time complexity? Well, the beauty of this algorithm is that it's one pass through, right? So we have to initialize a dictionary, just depends on the size of the character set, but then it's one pass through the string. You never have to go back and reevaluate and so on. So how long does it take? Well, it assumes that we can put things in and out of the dictionary in O of 1 time. As you're learning hash tables aren't always that simple, right? So, we teach people that, that hash table lookup is O of 1. But as you know, whether you're using the cuckoo hash or the double hash, it's not so simple. We have problems with collisions, right? So there are implementation issues. Also, hash tables need to be expanded. They don't always necessarily have enough room. Many of you have noted that if the hash table is not big enough, you end up getting collisions. Sometimes you can get a cycle of collisions where you can't even get out because the hash function doesn't cover all possible positions for a certain number. All right. So if assuming that these lookups, okay, so we have lookups a few places here, right? We're checking if it's in the dictionary. This is a lookup, and we're using the dictionary over here. We're using the dictionary over there. So 3 places using a dictionary. We're assuming we're getting, constant or near constant lookup time, but that's not necessarily guaranteed. And finally, we have one more encoding technique. The interesting thing about arithmetic encoding is that it's hard to find code for the arithmetic encoding. So if you go Google on Geeks for Geeks or other websites and you look for arithmetic encoding, you will find many implementations of run length encoding. You will find many implementations of Huffman coding. You will find many implementations of Lempel-Zeev-Welch. When it comes to arithmetic encoding, it's harder to come by. So I think Geeks for Geeks has an article on arithmetic encoding in MATLAB. Anyone use MATLAB here? You're majoring in math. You might use MATLAB. I don't know how much it gets used in the computer science department here. You've used MATLAB? MATLAB is a very powerful software for mathematical computations. I remember it already existing when I was in graduate school in math in Courant at NYU and back in the late 1980s. All right. So I think Geeks for Geeks has an implementation MATLAB, but even those of you who use MATLAB, I don't know if you're using it currently, but it's not probably a primary programming language. All right. So we wrote it in Python in my class during the year, different course, and networking course. We did it in Python, but I don't think we found a Python version. I'm sure if you look around, you'll find one. All right, so let's talk about arithmetic encoding. It's sort of a cool one. It's not necessarily taught so often. It's not as well known as the others, but it is important in certain contexts, right? So the basic idea is very different than what we've seen before. It's a probability. Okay, what we're doing is we're assigning a probability to a string, right? So in Huffman coding, you're assigning probabilities to each character, right? We just say, okay, I take the total frequency and look at the frequency for a little character. So that's the probability of a given character, right? But this also starts with that. So in a sense, arithmetic encoding and the Huffman coding start the same way, but then it changes, okay? Because what arithmetic encoding does is it encodes the entire string as one probability. Huffman uses the probability to encode each character individually, right? Using a variable length encoding. So the outcome of this is very different. Maybe the starting point is similar, but the outcome is very different. All right, so like everything else, the best way to understand it is with an example. Okay, so let's bring up our example here. All right, so we have 2 examples here. One example comes from the Wikipedia page, and the other example comes from the Faruzan, which is a book on networking. All right, so hopefully between the 2 examples, we'll get an appreciation of what's going on here. All right, so in both cases, we have a probability. Okay, what is a probability? The probability is associated with 3 characters. Now, it might be hard to read, so let me show you with my mouse. All right. We have, you see that little A there? Can you see an A? And you see a little B there and a little C. Okay, so what are we saying? We're saying it has been determined that there are 3 characters that possibly will show up in this text, A, B, and C. So maybe it's a little kid, right? A little kid who's like 2 years old. The little kid learned ABC, but all they know is ABC. They don't know the whole alphabet. They just know the letters ABC. Okay, I'm joking. But okay, they're just 3 characters, ABC, and the probability of A is 50%, probability of B is 33%, the probability of C is 17%. So far it's no different than Huffman, right? Huffman would also get probabilities or frequencies. But here's where it starts to get interesting. We say, okay, we're going to encode B. Going to encode B. Now, how do we encode B? We say, well, there's a 33% chance of being B, but we need an interval for the B. Okay. So what is the interval? All right. So the interval is a certain percent. You know what? Okay. So a B is what? It's between this 50% and the 83%. Does everyone see that? Right? In other words, getting an A is somewhere between the 0 and the 50, right? The B is between where you left off, the 50, and 50 plus 33 is 83. Okay, so that's what this picture over here is saying. This picture over here is saying, right? It's saying, okay, we're now between 50 and 83. Everyone see that? So far we got a B. So the cumulative probability of getting the B is, is in the 50 to 83 range. Okay, now it turns out that the next character is a C. So we say, what part of this interval is the C? Well, you have to multiply. So we multiply the size of this interval, which is 33%, times the 83%. Okay, why that? Because we're saying what part of my new interval? My new interval goes from 0.5 to 0.83, and I want the last part of that. So I say 0.83 times this interval. So I get to 0.77. In other words, 0.7739 is 83% of the way between 0.5 and 0.83. I'm going to say that again, right? We're trying to encode the letter C. C is the last 17%, right? It's from position 87% to 100%. So I take 83% of the distance between 0.5 and 0.83. That comes out to be 0.7739. And it's the last subinterval, so it ends at 0.83. So far I've coded the C and the B, and I have an interval of 0.739 to 0.83. Okay, now I get the A. The A is the first 50% of this interval. So what is half of the way between 0.7739 and 0.83? Well, it's going to start at 0.7739, and it's going to end not at 0.83. I think this is, that's a mistake. It should be halfway to the end. So halfway to the end, can someone do that? Someone do the math here? So I'm going to write it in the chat. We're going to do 0.83. It's sort of like merge sort a little bit. Minus 0.7739 divided by 2 plus 0.7739. Anyone want to calculate that for us? That should be the other end of the interval. I mean, we can approximate it. Okay, thank you, Chang. Okay, so that should really be the other end of the interval. Okay, so the last piece is to turn that into a binary number. Okay, so let's do some binary math together. All right, most of the time when we do binary math, we think of, integers, right? So we understand that 0 is 0. Let me write this way. 0 binary is 0, and 1-0 is equal to 2, and 1-1 is equal to 3. where should that correction be made? So I would say that number on the bottom right-hand corner should be 0.8, unless there was supposed to be another picture here that we don't see, but I did copy the whole picture from the Wikipedia. I would say that should be what Sheng said before. So it should be 0.80195. Okay, so let's just do some more binary numbers. Let's say 1101 in binary is equal to 841 is 13. All right, but we can also do this, and maybe you've never seen this before. You can also do this with fractions. So in what is that equal to? I'm going to answer that question. Okay, it's equal to that. What is 0.11 binary equal to? What's 0.11 binary equal to? Good. Okay, what about 0.111 in binary? Is that what it is? So it's going to be 0.5 and 0.25. Yeah, good. Okay, so you get the idea there. Now, it doesn't only have to be ones, right? You could do something like this. So I want to check that one out. So that's going to be 0.5 plus 0.25 plus 0.0625. Someone want to do that for us? Is that point? I think that's 0.83. What is 75? Yeah, 0.8125. Okay, so everyone see how you can do that with fractional binary numbers as well. So what we have here is we have an interval, right? The interval is based on our, someone want to read back to me what Sheng computed there? 0.80. What was after the, oh, thank you, 195. Okay, so that's our interval. And we need to encode that as binary. So we obviously need a 1. Do we need another 1? Yes, we do. Do we need another 1? Talk to me, because I don't want you to, you could write in the chat, I guess. All right, do we need another 1? So if I add another 1, I'm going to get, what did someone said it before? Someone said it before. Let's see. If I have 111 is 875. 875 is too big. So I'm going to need 0. That's not big enough. And if I do, it's going to be something like this, 0.11. 001 is probably right. I'm guessing that that's the right number. Okay, can someone calculate that for me? So it's going to be 0.5 plus 0.25 plus, that's 1/32. Okay, thank you, Daniel. All right, so you see that number there? That's right smack, not exactly in the middle, but it's in the middle of that interval. So what we do is we get the binary number, the smallest binary number that gets us inside the interval, right? Because what we're doing is we're encoding a string as a probabilistic interval. So we want to get a binary number that represents that, okay? So we're going to do another example, because again, this is by far the most tricky of the 4. It's not the most tricky algorithm that's out there. I mean, not the most tricky compression algorithm that's out there, but it is the most tricky of the 4 that we are looking at today. All right, so here's another example. This example comes from a book on networking. There's a chapter there on multimedia and compression. Why is, so there is a review question. One of the top hat questions involves this, but it will not be, you don't need to calculate one of these on the final, you know, in a time session. Okay, so I think there is one example in the review questions, and you can refer back to the example in our chat and so on. Okay, so can someone tell me before we go through this example, why would this appear in a chapter on multimedia? So this is from the chapter on multimedia in a networking text. Whereas if you were writing a text on networking, where would you put this? All right, so let me answer my question. So what is multimedia? Maybe you know the answer to that. When we say multimedia, what do we mean? We don't usually mean text, right?
Like combination of pictures, video.
Okay, things like pictures, right? Images, video, right? Music, right? So where is compression most important? It's always important, but it's most important when you're dealing with big. And big tends to happen with audio, with image, and with video. So where do you really need data compression most? You need data compression most when you're dealing with multimedia. It's not to say it's not important for text. And keep in mind that Lempel-Zeev and Huffman are primarily used for text, right? But in the in the scheme of networking, the compression, and remember, compression is not just about these algorithms. There's a whole series of lossy algorithms that we're not talking about, because again, this isn't, we're more interested in it from an algorithmic perspective. So lossy algorithms is another story, but that's why it's there. Okay, so with that, we have an example. Okay, they have their own style for representing it. I think they actually did a better job of, clearer job of how to present the information. Normally, I'm a big fan of Wikipedia, and I'm still a big fan of Wikipedia, but I think they did a better job of presenting this. Okay, so in this example here, once again, we have 3 characters, but in this case, the 3 characters are not A, B, and C, but they're A, B, and star, right? What are the probabilities? Okay, so again, we need a probability for each character. So the probability of an A is 0.4. You can see that there. Probability of a B is 0.9, and the probability of, I'm sorry, not 0.9, probability of B, you can see it on the bottom, but you could also see if we're taking the difference, is 0.5, and the probability of a C, I'm sorry, not of a C, of a star, of an asterisk is 0.1. So again, the probabilities appear on the bottom of the slide. All right, so what do? Well, we start at the beginning of the message. So the beginning of the message is a B, and we say, okay, the part of the interval that I'm concerned with is highlighted in orange. Okay, I guess it's sort of like orange, beige, brown. So what part is that? That's the part that goes from 0.4 to 0.9. So this becomes my interval. On the next one, I get another B. So I say, okay, the B is 50% of, it's not the beginning 50%, it's not the end 50%, it's sort of the middle 50% of whatever interval I'm at. So I say, okay, my interval is 0.5, and I multiply that by 0.5. So 0.2 into that interval is where the B is going to start. And it's going to end, right, 0.1 from the end. Okay, so again, if my interval is down to 0.5, 0.1 of 0.5 is 0.05, so it ends at 0.85. So what I'm doing is I'm saying, take my previous iterations interval, right? That's what I have over here. Take my previous intervals length and prorate that. Say, okay, I need 50%. B is 50% of whatever interval I had before, and it has to be the right 50%. So the right 50% is not the beginning, it's not the end, it's 50%, it's 40% of the way in there. It's 0.4 from the beginning. So 0.4 of the beginning of something that's 0.5 is 0.2 into the beginning. Now this becomes my interval. In the next case, I have an A. So the A says, give me the first 40% of that interval. So that interval is going to start with 0.6, and it's going to go 40% of the way here. So the whole interval is 0.25. 0.25 times 0.4 is 0.01. So my new interval is going to be 0.1, 0.1. So this is my new interval. Then I get another B. B says, give me the 50%, 40% of the way in. So 40% of the way in to here is give me 1 second there. Right, the whole interval is 0.1. So 40% of 0.1 is 0.04. So 0.4 after the 0.6 is 0.64. And it's going to go 50% of this. So we're going to have, if this is 0.1 in width, this is half of that, 0.05 in width. So that's why I get the B. And finally, the probability of the star is what? Is 0.1. So I say, here's my interval. My interval goes from 0.6 to 0.69. 1/10 of that interval, and this is 0.05, so it's going to be 0.005. So my new interval width is going to be 0.005. All right, so that's my interval. So let's do the binary on this. Okay, so do we need a 1? Oh, Key already got it for us. Okay, so if you look, 1011 rather is 0.6875. Everyone understand how to get that? So it's 0.5 plus looks like we're skipping the 0.25 because that would be too big. So plus the 125 plus 0.0625. And that will get me 6875 will be actually smack in the middle of this interval here. Okay, and then I have one more slide here. So at some point, I was looking for information on Lempel-Zief-Welch, and I Googled it. And I found this on Chegg. I said, my, that looks really familiar. That's my exam. So someone posted my exam on Chegg. Isn't that nice? Okay, it felt very important. All right. So let's just go back a slide here. All right. Let's do another example. Let's do another example. Okay, so let's pretend today that we are sheep. Okay, so we are going to encode ba. It's sort of like a Cheng, it is a little bit like a conditional probability in a certain sense. It's like it's a combined, right? It's combined probability. That's what it is. It's saying what's the probability of getting a B and then a B and then getting an A and then a B and then a star, right? So that probability will have a certain interval associated with it, right? Okay, the difference is, but here's the difference. See, the probability, it's an interval, right? It's more of a cumulative effect. So the probability of getting a B, B, A, B star is actually not between 0.685 and 0.689, right? Or whatever that number is on the bottom. And 0.69, okay? Probability of getting that is actually pretty small, right? Because it's going to be 0.4 times 0.4 times 0.5 times 0.4 times 0.1 is actually a tiny number, right? So it's based on this interval concept, okay? And the width of the interval represents the combined probability. Okay, did you catch that, Cheng and everybody else? Right? The width of this interval, which at this point is 0.005, right? So the width is a 0.005. So that is an approximation of the combined probability here. Okay, so we're going to try to encode ba. Okay, we're going to be sheep. Okay, so what is my interval for B? Want to write it in the chat? That's the easy part. First one is easy. 0.4 to 0.9. Good. Not 0.4, 0.4 to 0.9. Okay, good. Now, if I want to get an A on top of that. So that's going to be the first 50% of 0.4 to 0.9. So it's going to be 0.4 to 0.65. Did I do that correctly? Halfway, that's 2.5. So I think that's correct. So that's for BA. That was for BA. BA was 0.4 to 0.65. Okay. What about the A now, right? I need another A. So the next A is 50% of that. So my interval is 0.25. Half of that is 125. So my interval is going to be 0.4 to 525. That's for BAA. Okay. So our sheep like to work in the interval 0.4 to 0.525. Right? Can someone get us a binary representation of that interval, please? So what's the first digit going to be? 0 or 1? You're saying BA is 0.4. No, BA, if let's see if maybe I made a mistake, is B was 0.4, 0.9. A is 0.5. Oh, you're right. A is, you're right. I'm sorry. A is 0.4. So 0.4 is 0.6. Point was 0.2. You're right. You're right. I'm sorry. So it's 0.4. My methodology was right, but I wasn't remembering things right. Okay. The probability of the A is 0.4. So 0.4 of the interval is 0.5. 0.4 times 0.2. So you get 0.6. So that's for the BA. And now we do 0.4 of that. So that interval is 0.2. Its interval 0.4 of 0.2 is 0.08. So it's going to be 0.4 to 0.48. BAA. Someone want to double check that? Is that right? Who correct me? Was that Cheng? Okay. All right. So we need a binary representation of that interval. So this time I'm going to need a 0.0 at the beginning, right? 0.0 is 0. And then I'm going to do 0.01 will give me 0.25. And if I do 0.111, I get 0.375. And if I do 0.111, I get 0.375, 0.375, and 125, 0.0625. So it's going to be 0.43. Going to be very long. Let's see if we can find a, maybe we can find online. You got it? Key, did you do that by hand or you have a nice thing for us there? Well, let's see. What interval were we trying to get? Anyone have the, let's look at the original thing because you want the shortest one that you need. So we need between 4 and 4/8. So Qidong, I think, should work, right? We'll find out. My, come on. Now we need a fractional. You have a website that you used? All right, we'll just do it ourselves. We have more messages? Okay. Why is it not showing up?
I need to scroll down a little bit. It sounded there.
Scroll down.
Yeah. Yeah, right there.
Okay, so what did we have?
Scroll down a little bit more. You'll see the results.
Okay. So we're taking a binary number. Okay. Yeah. So the thing is, we need anything in this interval. So this is here's what we're going to do. We're going to do start. Come on.
I think that's an advertisement.
That's an advertisement. Okay.
Yeah.
Where did it go?
Scroll down a bit more. Yeah, right.
Okay, so this is a result, but we're not done yet. Okay, let me show you why. Okay. I can do it in the chat. Okay. Come on. Okay, so this is our 0.4. Now let's go back and look at 0.48. Nice converter here. Okay. Now run it again. So let me do it again.
Wait, I'm not too sure what happened.
So I'm saying, how do I run it a second time? Do I need to, guess I can always do that.
Oh, I think there's an error. Maybe try the one Codon sent, I guess.
Okay, start now is good, right? That's what we want. That's my advertisement again.
I don't know.
Is that?
Wait, maybe try this one, I guess.
Hold on.
The one other student sent probably working better than this one.
Okay. Go back to the chat.
Yes.
Okay, but that's using the answer. Okay. So that's in the range. Is that in the range, someone?
Yeah, I think that's in the range between
Okay.
24 and
Well, what you could do with your calculator is let's assume that if we actually press the button, it would give us the answer. So you could say here, take the 0.4, take the 0.48, and look at what they have in common. Right. So take the piece that's that's common, meaning it covers both endpoints, and you use that, and then ignore the subsequent digits. Okay, so we're going to stop here. I can stay on if people have questions, but that's the end of our lecture. And what was the top hat for today? Thank you. Assignment 4 in this course, yeah, I think. Anyone confirm that?
For the simple web page, yeah, I think you
Wait, no,
did.
not simple web page. No, this is 323.
Oh, that's right. That's the hash function.
Yeah, hash function trees. You should look for it. It wouldn't be a PDF. It would be the announcements page. Check the announcements page. You don't have any. Do we have a PDF? I don't think we even have a PDF.
It's not in the assignment page, but it's inside the announcement
Announcements,
page.
right? On the announcements page. So I mean, 4 and 5 were due, but we've extended it. So if you get it done, be nice if you get it done, let's say by tomorrow night. Friday I don't teach, so I have time to grade stuff. You may find, some of you, that if the strings are like taking too long to run, so if you need to, you can shorten a string, that's okay. Don't cut the list down, just take an individual string that's like too big and you can make it shorter. Just keep in mind that the palindromes are palindromes. You cut down the palindrome, it's just not as much fun, but. All right, so Young Ying wants to share PyCharm. Yeah, you can share PyCharm. So again, if you could try to get the 4 and 5 due, try to get them done on Thursday, Friday morning. So I would like to work on grading them. Okay, so some people have had problems. I'm sorry for this. The format is a problem. So you need to change the encoding. So you were able to, you fixed that? You're able to deal with that? Just enable your mic so you can talk to me.
Yes, Professor.
Okay.
I changed the right here, but let's run it.
The sound is not coming in very good. I don't know if you can, it's something you can do about that.
Okay, I run it again. Can you see me?
I see your PyCharm very clearly. Okay, so what are we trying to fix? Are we trying to fix the no such file or directory? Is that the problem?
Discussion.
Okay, so it's saying
No such
it
file.
doesn't file because you need to look in today. Okay, so either get rid of today or move or change the name. Where are you passing the file? Where are you passing in palindromes.txt? Where in your code? Search in your code. No, go to your code. Go to assignment 5, please. Go click on the tab for assignment 5. No. Okay, fine. Do you want to do it there? Find palindromes.txt. Where are you calling it? Use Control F. It'll go fast. Okay, process file right there. So you have your code is nice and organized. I like it. So instead of palindromes.txt, put the word today before the word palindromes. Right there. Put the word today / not today with a Y, today. That's your word. I don't use the word today in my code. Okay, do the same thing with sentences, please. And if that doesn't work, you might need a longer path, but let's start with that.
Wait, but I think PyCharm should automatically detect. I think the
Alright.
problem is the encoding when she's trying to open the file. I'm not sure why include
Problem is
all.
the encoding is saying no such file.
This one encoding.
Yeah, I didn't use that myself because
Okay.
that's not what's included in the code you gave.
Okay, so let's click on palindromes.txt. Okay, and
I see
on
window.
the bottom, okay, can you change that? Click on that. Oh, it
Change-
should be 1252. Go back to assignment 5. Go back to the code. Go back to the code. 1252. The other one also. Are they both 1252?
Yes. Oh,
Okay,
no.
so fix the other one, please. Fix the, no, go back to the code. Go back to the code and fix the other one. Line one, no, no, no. Go up, go up, go up. In line 123. Why do you have 2 copies? That just delete that line. We don't need that line. Delete it. Okay, delete. Okay, now go down to the bottom. So the today was my bad. Get rid of the today because your assignment is already in the today directory. So we don't need that already. It should know that. That was my bad. Okay, right click, run. Okay,
Still not release the file.
okay, wait, go down to the bottom. Go up. Okay, what happens if you remove the encoding?
Ah,
Change. What happens if you remove the encoding? Go up. Just remove the encoding for a second. Just take it out.
take out all the stuff.
Yeah, yeah.
What is the R? I'm not too sure. What's the R?
The refile, right?
Okay,
Because I didn't use that and mine's worked. So
the R is okay, it means to read. That shouldn't be an issue. It's saying palindromes.txt. Can you right click on the palindromes.txt on the left side there? Right click on that. Refactor. Rename. Palindromes. Looks like it's spelled correctly. Just make sure there's no space after the TXT. Just
No space.
move your cursor. Keep going. Okay, so that's fine. Okay, cancel. All right, let's open up, double click on the palindromes again. I don't know if the encoding is a problem. And change on the bottom to UTF-8. UTF-8. Okay, and it should save it automatically, I think. Do that for the sentences also. Okay. And now try to run it. Just try to open the sentences instead. Okay, so change to 140, uncomment 40. Do we get the same error for both?
Yeah. For both.
Okay. Okay, let's see.
we can see she put the spaces behind the assignment directory. I'm not too sure if that's gonna help. if we
Where do
move it.
where do you see that?
In the console, you set in the arrow in the path for the assignment 5. Before that, she have some spaces in the directory name assignment 5. Right, you can see that space.
Oh, where did that come from?
I don't know, she can probably rename the directory. That gonna
Yeah,
help?
yeah, maybe, yeah. So right click, go move your mouse to the left, left, left. Move your mouse up to the left. Keep going, left.
Yeah.
Go up, no, up,
The folder,
go to the folder on the left side. Left, right there, up one more to ASS5, right click, refactor. Rename. Okay, you got some blanks there. I don't know if that's an issue, but it's a good catch. Just, okay, you got rid of those spaces?
Yeah, no more space.
Okay, refactor, press refactor. All right, I don't know if that's an issue, but you don't really want to have spaces at the end because that could be confusing.
Hmm.
Look at that.
wow.
Oh,
I don't know,
Wow.
that can be a
Who
issue.
would have thought? Thank you.
thank you.
Okay,
Okay.
it's a very wide table. Someone else said that also. I don't know. Is that because of the encoding also?
No, it's
No,
because the last line.
because the last line of the palindrome was
Last
too
one was
long.
very big.
Yeah,
It's
because
very
the
big.
last line is like have a
very big.
huge, yeah, it's a huge line with commas in it, so it's like a
Uh-huh.
lot of words.
All right, okay. All right, it is what it is. All right, good. See, little nothing, huh?
Thank you so much.
All right, thank you to our students. Good catch.
Professor,
Do you know what Pareto's inequality is? Pareto's inequality is that 90% of the wealth is by 10%. Now they call it the 1%, right? So that inequality applies to a lot of things. So like you spend like 90% of the work on 10% of the problem. Yeah.
yeah, I solved the problem by changing my system languages. Like instead of the local language, we changed to English, then it works. I don't know why.
Oh, really?
Yeah.
Okay. All right. Yeah, these little glitches. I mean, I spent a lot of time in industry. We spent a lot of time on the silliest little things, and the hard stuff went much faster. Okay. All right. Any other questions for today?
Professor, I forgot to punch in the top echo for the 355 class. Is that can you make an exception for today?
Yeah, you deserve it because you get good
Sorry about that.
good contributions. You make your presence well known with your contributions. Appreciate that.
So how should I do that?
I'll take care of it.
All right, thank you, Professor. Have a good day, I guess.
Okay.